It is the Shor's algorithm. So this is a major algorithm that triggered the study of quantum computing research. When Shor proposed this algorithm, people find that, hey, this is going to be transformative, and because it's going to break all the conventional encryption system. And that's why this is another reason why people start spending a lot of effort in studying quantum computing. I think it's in about 1995 or 1996. And other important milestone also by Shor, he showed that it's possible to do quantum error correction, not about this algorithm, but in general. And people also start at that time to realize that it's possible to have a quantum computer, because before that they thought that the error will just keep propagating. You can never correct it, so it's not going to be useful. So Shor's algorithm is difficult, of course. We will only have some superficial understanding, right? But on the other hand, its implication is big. So let's try to understand the background first. Why this is important. So we'll first talk about factoring and period finding, right? So first of all, currently, right, the major encryption in our classical world, which you are using every day when you send messages, you do your banking, they is something called RSA scheme, right? I think it's the initial of the three inventors. And the encryption process is related to prime factorization. So what does it mean? If you want to decrypt something, basically, it is asking you to try to decrypt an integer, an n, right? So your goal is to find two integers, but it is prime numbers, right? You need to find two prime numbers, P and Q, okay? So that n equal to P times Q, right? As an example, easy example, if you are given 21, you need to find out is integer, is prime factorization. What is that? Which two prime number give you 21? 3. Thank you, right? It is 3 times 7, right? So, which is P times Q. You know it is 3 and 7 because you have memorized the the multiplication table, right? Or you have used it very often in your daily life. But in principle, the way you do it is try to divide n first by 2. See if that works. Divide it by 3 and then find that, 3 works, right? If 3 is not a prime factor, you divide by 4 all the way to square root n. And then you know what it is. But what if this n is 100 digit, right? 100 digit, right? 1 trillion is only what? 12 digit, right? If I give an n that is 100 digit, can you find its prime factorization? Okay, so in this encryption process, it is like this. If you have the password or you build up something with the banking, they have the key, which is probably something you can find or one of the prime number. They can easily find out what is the another one. But for anyone who doesn't have the private key, it will be very difficult to find the prime factorization. As a result, they cannot crack your encrypted message, right? So, which I don't know this well, but just trust me, right? Encryption is related to prime factorization. So now it comes to the point that if you can factorize a number to find its two prime factors, then in principle, you can easily break any encryption that we have. Okay, that's the first thing. Now, but then mathematically, prime factorization is also related to the period finding of this function. A little bit complicated. F subscript a n of x, which is a to the power x modulus n. Right? So very complicated, but you do see that it has the capital N. So basically, if you can find the period of this function, you will be able to factorize n very fast also. Okay, so it breaks down, it transforms the complicated question to back to like, if you can find the period of this function, everything else will be easy. But finding the period of this function, again, is very difficult, right? But first, let's understand what is the meaning of finding the period of this function and what is the meaning of this function. I think some of us are not familiar with this number theory, modulus n, right? But anyway, let's just mention that a, n, x, they are all integers. They need to be integers in this, right? And then we also pick a. Okay, so a is not given because you see that x, of course, is an independence variable. 1, 0, 1, 2, 3, 4, 5, 6. This is the independence variable. And f is the function. It's related to n. But what is a? We will pick a randomly. Okay, so now you give you any a, you find the period of this function. Okay, so let's just look at an example. So, of course, I also need to mention the meaning of this, right? What is the meaning of ax mod n? It means find the remainder of ax divided by capital N. Right, so ax, a to the power x is an integer. It is divided by capital N. Sometimes it's divisible, right? When it's divisible, what is the remainder? 0, right? Otherwise, it can be other numbers, right? Again, let's look at an example. For example, if a to the power x equal to 16, and then n equal to 6. So what is ax modular n? Someone say 4. Why? Because a to the power x equal to 16, it is equal to 2 times 6 plus 4. This is 2n. Is this okay? Yeah. So very simple, right? It is just the equation or the symbol looks very confusing. But after all, something modulus n means that you divide by n and find the remainder. Any questions? Yeah.
So the only part that's kept is the remainder?
Say again, sorry. Correct. So this is a whole function. Then the output is 4, which is the remainder. You're right. So we don't care about the quotient, etc. Just the remainder. Okay. So good. If you're okay, then let's continue. So let's just consider this function because we try to factorize 21, right? So let's consider capital N equal to 21. And we pick, this is up to you. You can pick any A, okay, in order to solve this problem. But I pick A equals to 11, okay? Randomly. I pick it randomly. Okay. So now what is f of a n x? It basically is f of 11, 21x, right? Because now A is 11, right? N is 21. And again, it means that this is 11 to the power x modulus 21, mod 21, right? So basically now is that we want to try different x and find out what's the remainder when it's divided by 21. But our goal is to find out its period. Why it turned out to be a periodic function. If I know its period, then I can find out the prime factorization of 21 very fast. Okay. So let's try one by one, right? So let's start with x equal to 0. Then f of 0, x equal to 0, right? Equals to, can you tell me what is f of 0? Based on definition? I mean, give me the expression first. 11 to the 0 mod 21. Thank you. And he said it is 1. Do you agree? Because 11 to the 0 is just 1 mod 21, right? So 1 divided by 21, of course, not divisible. So the remainder is 1. The quotient is 0, right? 1 equals 0 times 21 plus 1, right? This is because 1 equals to 21 times 0 plus 1. So this is the remainder. Is this clear for this step? Okay, so now we go to another step. X must be integer, so we only care about x equal to 1. Then what is f of 1 by definition? 11 to the power 1, thank you, mod 21, right? Which is 11 mod 21. What is the remainder for this one? 11, right? Because 11 again equal to 21 times 0 plus 11, the remainder, right? Very boring. So let's continue. Do one more time. When x equal to 2, f of 2 equal to what? 11 to the power 2 mod 21. So this is 1 to 1 mod 21, right? What is this? Wow, you guys are really good. I need my cheat sheet. Yes, it is 16. Because 1 to 1 equals to 5 times 11 plus 16. The remainder is 16. Let's pause here. Is it okay so far? F of 2. Again, f of 2 means this. And something mod 21 means find the remainder when you use this one divided by 21. Questions?
We haven't seen the period.
Haven't seen what?
The period. What is the period?
We have not found the period yet. I just pause here. And very good. No period yet because f of 0 equal 1, f of 1 equal 11, f of 2 equal 16. I still have not seen it repeating, right? So we don't know the period yet. But are you okay with this math? I likely won't test you, but I would like you to understand the background. This number theory are good to hear about and learn a little bit. Okay. So if that is the case, you will continue x equal to 3, but that is too much. I'm not going to go through the math, right? You just go home, try Excel, and this is 8. Okay? X equal to 4, f of 4, 10 to 11 to the power 4 mod 21, and the answer is 4. Okay? f of 5, and these are difficult to calculate. You see that every time actually to find the remainder, you need to do a division. And f of 5 equals to, you may do many division. F 21, this is equal to 2. X equal to 6, f of 6 equal 10 to the power 11 to the power 6, right? So you really need to do a lot of exponential. It's computational intensive, right? We're only doing 21. What if it's 100 digit number, right? 21. And what is this? This is 1. Nice. So you see that the remainder, right? It goes from 1 to 11 to 16 to 8 to 4 to 2 and then to 1. And based on number theory, it will repeat. It's going to repeat 11, 16, etc. So what is the period? This is x equal to 0. This is x equal to 6. So you do this 1, 2, 3, 4, 5, 6. Right? So you see that the period R, we call it R, equals to 6. Now this is a tedious process, but once I find the period, I will be able to factorize n easily based on theory. Okay? Any question? Yeah. Yes, it's guaranteed. Yeah. Yeah. Just because of the number theory. Yeah. Okay, great. Right? Any other questions?
So you mean that for every function, there is always a period?
There's going to be a period, yes. Yeah. It's just whether it's long or short. Yeah. Good, right? So then what? So now we are going to see something more confusing, maybe, and some more theories, okay? First, a to the power 0 modulus 1. What is this? No, modulus n. Equal to what? We just had an example, right? A to the power 0 is what? 1. 1 modulus any number larger than 1 is what? 1, right? But 1 divided by any integer except 1 has a remainder equal to 1, right? 1 over n equal to 0 times n plus 1. So equal to 1, I wrote it already. Now there's another way we can write it. We can also write it as A0 equals to 1 mod n. So that becomes another type of arithmetics that we say that this equal to 1 in the mod n domain, right? We only care about the remainder. So if two numbers, right, they have the same remainder, in this algebra, they are the same. Right? That is, I forgot all the basics, but that's a part of the number theory. Okay? That why I say that, for example, if the period is R, right? If period is R, what does it mean? It means A R mod n equal to what? If the period is R. Forgot what is the period, right? Period is what? First, the function is a to the power x, right? So if f of 0 equal to 1, Then after the period, what will be the answer when you mod n? Also 1. And that's the definition of period, right? So this is also equal to 1. Okay? So you also can write it a to the power equal to 1. But you need to make it clear mod n. But if you know that you're talking about mod n, you can remove this. So a to the power 0 equal to 1, a to the r to the power r equal to 1. We are not saying that their integer value are the same. We are saying that when they are divided by n, their remainder are the same. Right? That is the meaning of this statement. And again, why a to the power r need to be 1? Because this is the period. So at a equal to 0 equal to 1, because 0 is x, right? Then after r period, it should be 1 also. Any questions? Make sense so far? If it's confusing, please ask, right? I know there are many new things here. Okay? So now I assume you are okay with this. So if you are okay with this, then we will further just, if you look at these two equations, right? Maybe 2 minus 1. It becomes a to the power r minus a to the power 0 equals to 0, of course, mod n. So you accept it because we did not study the theory, but that they do have something very similar to normal algebra. If I don't have mod n in normal algebra, a to the power 0 equal to 1, a to the r equal to 1, then of course left-hand side subtract to get, r a to the power r subtract a to the power 0 equal to 1 minus 1, right? So this is equal to 0, right? But in this mod n, I don't know how to go, domain, right? It is still the same, right? We just say, remind us that, and basically what it says is that a to the power r minus a to the power 0 divided by capital N has a remainder equal to 0, means it is divisible by capital N. Okay? And which makes sense, right? Because the remainder of a to the power r divided by n is 1. So you subtract 1, then you divide it by capital N. Well, of course, it's divisible. Okay. Now, then we can continue to use the regular equation we have learned. This can be written as to the power r divided by 2 plus 1 times a to the power r divided by 2 minus 1 equal to 0. Of course, again, we're talking about mod n. Do you see that? Because this is just a plus b times a minus b. Or what I'm trying to say is, this time this becomes a to the power r. 1 times negative 1 actually is just a to the power 0, right? And then this negative a to the power r divided by 2 cancelled by positive a to the power r divided by 2, right? You just expand it, you get the same thing. It's just a regular algebra. We do this so that we can think it in a way like what we think in regular algebra, although we are talking about modulus n. And then this is the theory, right? If R is even, okay, R's need to be even, and a to the power r divided by 2 plus 1 not equal to 0. And when we say this, of course, still talking about modulus n, right? We're saying this one not equal to 0, right? Means that this one divided by capital N has remainder, right? But doesn't matter. Now we just forgot modulus n. It's just like saying that this term times this term equal to 0. And if this term is not equal to 0, means kind of like something special, right? If this happen, okay, then the prime factors of n are P equals to GCD of A to the power R divided by 2 plus 1 and n. Q equal to GCD of A to the power R divided by 2 minus n. I was saying many things. So, what is GCD? Anyone remember? Thank you. Greatest common divisor. Okay. So, if I find out the period of this function, which is R, and it happened that R is even, so the period can be odd. If it is odd, what do? Try another A. A is somewhere we randomly pick. We pick another A, find the period again. If it is even, okay, great. And also, you need to make sure that A to the power R divided by 2 plus 1 is not equal to 0, modulus n. Okay? Or in other words, this is not a multiple of n. Right? If that is the case, you can find the prime factor of capital N as this. It is the common greatest divisor of this guy and n, and also this one and n. That gives you P and Q. This one is fast. To calculate this one, GCD is fast. Right? So once I find out the period, then I can easily find the GCD of this number, and then I can find the prime factor easily. Okay? Now that's something very important. If this has a very low chance, it's not going to be useful, right? So we would say for A smaller than n, 50% of chance we get even R and AR divided by 2 plus 1 not equal to 0. Right? So how often do we get this? 50% of the chance, which is good. Because if I have an algorithm to help me find the period very fast, even I don't have this every time, but I have 50% of the chance that I have this, then I can find the P and Q very fast also. Okay, so I am sure that you don't know what I'm talking about so far, right? Which is okay. I will go back again to give you a big picture again later. But for now, let's just play with the GCD. How do you find the greatest common divisor? For example, for n equal to 21, okay? We already showed you, right? We pick A equal to 11. We get R equal to 6, remember? We pick A equal to 11, and then we try to find the period. We find out the period is 6, right? That's what we got. So because of this, I want to find the P, which is the GCD of A to the power R over 2 plus 1 and n. What is A to the power R over 2 plus 1? It is 11 to the power 6 divided by 2 plus 1 and then 21, which is GCD greatest common divisor of 1, 3, 3, 2, 21. First of all, do you understand what I'm doing here? I want to find based on the theory here, P equal to GCD of A to the power R divided by 2 plus 1 and n. Right? And that's why I substitute. A was 11, when a equal to 11, for this function, r equal to 6. So 11 to the power 6 divided by 2 plus 1. And then n, 21. This one, if you do the calculation, 11 to the power 2, 11 to the power 3 plus 1 equal to 1332. Any questions? Do you still remember how to find GCD? Use Euler algorithm? Maybe you know, right? I also forgot when I was teaching this class. So we use, you don't need to learn it, but it's good to review. Not Euler, sorry, Euclidean algorithm. So what you do is this. There are many different methods. That's what I learned in school. You put 1332, 21. And your goal is to put the remainder at the center. So here is the quotient. Right. This is quotient. And here you put remainder. So the first thing I will divide 1332 by 21. Okay, so to do this, I start with 6. This is 12. 126. So this gives me 2. And then this gives me 72. So I divide by 3. This gives me 63. So this gives me 9. Right? So 1332 equal to 63 times 21 plus 9. And therefore, I put 63 and 9 here. Make sense? Yeah, but if you forgot, of course, you don't know what I'm talking about, right? Then you just get the result. Now, I need to divide 21 by 9. That is easy, right? It is equal to 2 times 9 plus 3. 2 times 9 plus 3 equal to 21. Then I continue. Now, I want to divide 9 by 3. What is this? It's 3 times 3 plus 0. So I'm done. And the greatest common divisor then turned out to be this. This is the GCD, the last remainder before 0. Okay? So then what does it mean? This equal to P. P equal to 3. Okay? So let me do the same thing to find Q. Q equals to GCD of a to the power r divided by 2 minus 1n, which is GCD of 11 to the power 6 divided by 2 minus 121, right? You do the math. This will be 133121. Sorry, should be it's 133. 0, sorry, yeah. 0. The difference should be 2. Thank you. 133021, right? So I do the same thing. I write 133021. So first I need to divide 1330 by 21. Based on what I got earlier, this must be 63 still. But then the remainder will be 2 less, right? It will be 7. Then I try to divide 21 by 7, which is 3. 3 times 7, okay, remainder is 0. So again, the last non-zero remainder is 7. This is the GCD we are looking for, and this is Q. And do you see that in the N equal to P times Q equal to 3 times 7? So I have done the prime factorization, right? So if you forgot this, that is fine. Go back. I won't test you the algorithm in exam, right? But it's good to recall. But the main point here is that once I find what is R and what is N, what is A, or another way, I find out what is R, I can find the prime factor of n very easily. Euclidean algorithm is a very fast algorithm. Even your number increase to 100 digits, it grow up, I don't know, actually maybe linear, at least not exponentially. So you can do it very fast. Okay, so let's go back to what we have been doing again. Our goal is that there's something called encryption, very cool. And encryption is related to prime factorization of a number. The prime factorization can be done if you can find out the period of this function. If you can find the period of this function as I show you, then I can find the prime factor easily using the greatest common divisor by finding the greatest common divisor of these two pairs of number, right? So now we don't need to worry about greatest common divisor. What we worry about is how to find the period of this function. Because if I can find out, then I can factorize the number. Then I can hack any password easily. Make sense? So after all, our goal is to find out the period of this function, a to the power x modulus n. And n is given. X is independent variable we want to find the period from, right? A is something you need to pick, you need to guess. Now luckily, 50% of the chance will give you a that is good enough to use this equation. 50% of chance you get some useless result. Then you need to redo it. So I give you a number that is 12567,912. There are many numbers, so you have many a to pick from. You don't know which one to pick. You randomly pick one. And you may be successful, you may fail. But you have 50% of chance to success, right? To succeed, right? And you just keep trying. You won't take too long to succeed because 50% of the chance will be successful, right? Okay? So let me just summarize what I just said. First of all, Euclidean algorithm to find PQ from given A, R, N is fast. Okay, so we don't need to worry about this part, right? But the point is, and as a result, finding the period of a to the power x mod n is equivalent to finding n equal to p times q. Okay? If you want to factorize capital N, you just need to find the period of this function. Because with the period of this function, then I can find P and Q easily using the GCD. Okay? So that is the summary of the background. I talked about a lot of background. Right. Now we go to the quantum algorithm. We use Shor's algorithm to find the period much faster, exponentially faster. Okay? And that is the purpose of Shor's algorithm. It doesn't do the factorization for you directly. It finds the period. When it finds the period, then you can do the factorization quickly. And then you can crack all the encryptions. Okay? So, very busy, right? We'll go through step by step. But before that, I would like you to appreciate what it is doing. First of all, you have a quantum oracle again. And it is a function, right? Because it's y exclusive f of x. And guess what is f of x this time? of course, is related to the problem, right? Which is a to the power x mod n. That is what you need to put in quantum oracle. That's the first thing. So second thing, let's look at what it's doing. You have Hadamard gate to the power 2n, right? Means tensor product of 2n qubit. What is the reason of having Hadamard gate again usually? Create a superposition, exactly. And why? Why do we have to want to create a superposition? Because it will create exponentially many basis state, right? To the power n basis state. Then we pass it to the quantum oracle. What does it mean? You are doing quantum parallelism. You evaluate to the power n of them all at the same time. Yeah. And then you do some Fourier transformation. The reason is you try to do some constructive and destructive interference. So to let those related, some state come out, and they represent the period of this function. So like what we did in Deutsch algorithm, we say we did the quantum computation in parallel. We find f of 0 and f of 1, right? But we don't know what is f of 0 and f of 1. It just tells us that whether it's balanced or constant, right? But I still don't know what is f of 0 and f of 1. It is the same here. It only tells me what is the period. I still don't know what is f of 1, f of 2, f of 3, f of 4. Right? So again, in some sense, quantum computing is not really like something unbelievable in some sense. I mentioned this before. It's a conservation of information you can get for the given effort. You only get the period, but you don't know the rest of them. Right? So the God, the nature did not give you something extra actually, in some sense. Right? So again, let me remind you, classically, to find the period, I need to evaluate f of 1 all the way to f of 6. If you are a very big number, you need to do 1 million computation until you hit the period. But here, you quantum computing, you get out. You just want to get out. You don't know exactly what are the value of each of them. You only know what is R. Okay, so that is the idea. So, okay, so Shor's algorithm is for this purpose, and then now we start with the difficult math, right? But it's not difficult. Given n, I give you a capital N, okay? Okay, so in this algorithm, you need to have n qubits so that 2 to the power n larger or equal to n. Okay, but that is not everything, and you need free n qubit. Okay, so first you are capital N, then you find out how many qubit you need to represent the capital N, and then times 3. That is the total size of your circuit. For example, we just say that capital N equal to 21, right? Then what should be small n in that case? 2 to the power n larger or equal to 21. What is n? How should we pick n? N equal to
5.
5. Thank you. Because 2 to the power 1 is 2, 4, 8, 16, 32. 32 is larger than 21, right? 16 is less than 21. So I need n equal to 5. So I need, in total, 3 times 5 equal to 15 qubit. Quite a lot, 15 qubit to solve this problem. Okay, and you see that in this circuit, I do have two groups. The top, LSB, n qubit, the bottom, 2 n qubit. So the top is 5, bottom is 10, right? As an example in this case. Is that okay? Now I chop this circuit into many parts, right? We start with the first part, Z0. What is the work function? This one I could have put in midterm, right? What is the cat state for this initialized state? This is 0. What is this? How do we write it? What is the wave function? The state of at the beginning. How do we write it? Just 0. But make it very clear. 0, tensor product 2n, 0, n, right? It means I have 2n of 0 at the beginning for MSB and then n 0. So altogether I have 3n 0. Although this is very simple, but if you still feel confused, please let me know. Any questions? That is the beginning of this state, of this circuit. Any questions? Now, after that, we've gone through something, right? Which is the Z1. This is equals to, can someone tell me what does it equal to? There's an operator applied to Z0. How do we write the operator? Say again. H tensor product 2n, tensor product I, n. Do you agree? First of all, this is the MSB, right? And this is the LSB. So we apply Hadamard gate, 2n qubit Hadamard gate to this 2n qubit. And then nothing to this n LSB, which means we apply the identity gates to the top, right? Yeah. Any questions? Okay. So let me do substitution. And now I'm going to do some simplification. I just put this as 2n, make it clear. This one is applied to 0. Right? I'm going to remove the tensor product symbol, right? And then this is the bottom qubit. And the top I can just write as this. Because I is applied to this. I apply to this. H applied to this. So I have H applied to this and I apply to this. I get this. Sense? What is H applied to this? Well, you probably forgot, but you have the equation, right? Yes, 0 plus 1, but only for 1 qubit is 0 plus 1. But for 2n qubit, what is that? Just all the superposition of the 2n qubits, the Hilbert space, right? It is 1 over square root of the 2 to the power 2n. This is the number, the size, right? Summation x equal to 0 to the power 2 to the power 2n minus 1. I see something wrong. And then x, I just put 2n, so you know that this is the first 2n qubit, but I put it at the bottom, and then 0. Do you remember this one? When you do apply the Hadamard gates to n qubits, it will perform a superposition of all the possible states from 0 to the power 2 to the power 2n minus 1. We have 2n qubit, that's why 2 to the power 2n minus 1. Do you have a question? Very good. So he said that we should simplify this. That's right. It's 2 to the power 2n divided by 2, right? So very good. Yeah. So this one will give us 1 over 2 to the power n, and then summation x equal to 0, 2 to the power 2n minus 1, x. Again, this is just a label. And now I also put n at the bottom. I just want to say that, okay, just remember this is an n cubic 0. That's it. Some of you still feel confused, right? Let me know if you have any questions. Because if you cannot understand this, we cannot move forward. We're talking about how to get Z1. Any questions? The most important thing here is that you should understand how to apply the gate, right, or the unitary transformation to the correct matrix. Here is H and I, but you know that H applied to the first 2n qubit and I applied to the last 2n qubit. So the last 2n qubit never change because it's I. And H applies to the first 2n qubit. You just use what we learned earlier about Hadamard gate. We have a class talking about Hadamard gate applied to 0. Remember? It's an equal superposition of all the basis states. From 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, all the way to 1, 1, 1, 1, 1. Or this 2 to the power 2n basis state. Right? And in special case, when 2n equal to 1, right? I mean, 1 qubit, then what you have is 0 plus 1. You have 2 qubit, what you have is 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. Remember? Okay? Any questions? If not, I will move forward. Our goal is to find what happened when you go to 2. 2, of course, equals to the quantum oracle, U of F. The whole thing applied to 1, right? How many qubits do we have for UF as a quantum gate? This is how many qubit gate based on the drawing? 3n, okay? So it's 3n. It applied to whole thing. And based on the definition here, what happened to it? It keep the first 2n qubit unchanged, but the last n qubit, it will do exclusive OR with f of x. Yeah. For this one, which part? At this part or this part? Oh, you mean why don't I draw identity gate? Because when I don't draw anything, I assume it's identity gate, right? Because it doesn't change, right? So you're right. If when I say I here, it means there's an identity gate. But in reality, I don't apply identity gate. I just let the circuit sit there. Yeah. Okay, so let's play with this. So what does it say? So first of all, based on what I had earlier, I have 1 over 2 to the power 2n, right? X equal to 0, 2 to the power 2n minus 1. But I apply UF into this guy. Right? What I'm doing is that apply UF to this whole thing, but this is a superposition, right? It's linear. So I can matrix apply to the sum of vectors is just equal to the sum of the matrix applied to each vector. Is that okay? So what I need to evaluate here is this one. What is this? Of course, UF applied to x to the 2n, 0n. Based on this equation, it says that, okay, this is still x 2n, but then I will have y, which is 0, exclusive or f of x n. Make sense? I'm using this equation. What is this? 0 exclusive or something? Just that thing, yeah, something, right? If 1 exclusive or something is negation, right? Not gate, right? We mentioned this a few times. So this is so simple as this. Okay? So based on this, then I would say this equal to 1 over 2 to the power n summation x equals 0, to the power 2n minus 1 x 2n f of xn. Do you see that this is a parallel computation? If I have 40 qubits, I have done 1 trillion f of x computation in one shot. Because this is a superposition of 1 trillion basis state to the power 40 basis state. Make sense? Right? And that is where you have this quantum parallelism. Or of course I cannot get them because this is the basis state, right? It's all there. Right? I don't know what this is, but they computed already. They exist there now. And now that to be smart to extract the period from this. And that's why we have quantum Fourier transform after that. But this is like superposition and then followed by parallel computation. Any questions? Okay. So I repeat the function here. This is C2. Okay. So let's continue. What happened when we go to C3? Now, based on the drawing, right, and what do we have this time? We actually have a quantum Fourier transform gate, which is a 2n qubit gate. Tensor product with identity gate, which is n qubit, applied to Z2. I don't know how to write it, right? But are you okay with this? This is C2, right? That is this part. Again, we recognize it's a superposition of many basis states. Each basis state is 2n qubit tensor product with another n qubit. But this time we again apply this, but as you can see earlier, this is going to apply to x only, right? We are not going to apply to f of x. So if I get this into it, I get 1 over 2 to the power n summation x equal to 0 to the power 2n minus 1. And then I can say, okay, this quantum Fourier transform is n qubit only applied to x 2n. And then we just leave this f of x unchanged. Right? So what I'm doing here is I apply this to here, right? So to the whole thing, right? But again, it is linear. So I will distribute this matrix into the basis state. So I have 1 over 2 to the power n summation, take it out, right? And then I apply this one to each of these terms. But this is only to first 2 qubits. So I only apply quantum Fourier transform to this first 2 qubits. The last n qubit will keep unchanged. Okay? Any questions? But do we know how to find this? We just learned it 2 weeks ago, or a week ago, right? We just learned the quantum Fourier transform, right? There is an equation. Maybe you forgot, that is fine, right? No one asked you to memorize. But if you remember, it is going to be this. Let me just write down everything outside first. This is just repeat what we had. To the power 2n minus 1. Quantum Fourier transform, if you remember, it is, again, you need to normalize it to the power 2n divided by 2, because this is 1 over capital square root capital N. And remember what the matrix is? This goes from 0, k to equal to 0, to the power 2n minus 1, omega negative kx, k. To n f of x n. So actually it is here. Here, quantum Fourier transform. This is the equation we learned earlier. Do you remember it was a summation of every state? And every state is weighted by omega to the power minus ij, right? But here is kx due to the index. So that is what I put here, right? So quantum Fourier transform of x is equal to the summation of all the basis states, but weighted by omega negative x times that index k. That's it. Okay? So this is also not difficult. It's just math, right? So I just combine them together. This is 1 over 2 to the power n again. Then I combine with this one. It becomes 1 over 2 to the power 2n. First of all, then I keep this one summation x equal to 0, 2 to the power 2n minus 1. I take out this summation k equals 0, 2 to the power 2n minus 1, and then omega negative kx, and then k, 2n, and then f of x, n. It's just long, but it's not difficult to understand if you go through step by step, right? So now I have a lot of superposition. Okay, so up to here you may get lost. You forgot what we have done in math, which is perfectly fine, right? You only need to know that we do superposition, we do quantum parallelism, and then we do quantum Fourier transform to come up with this. And you need to understand the math, right? When you follow it, you understand it. Then I think that's the requirement. You don't need to memorize the step. Okay. And now, this is what I just showed you in C3. This is now the wave function after this oracle and quantum Fourier transform. What we're going to do is to do two measurements. The first measurement is on the least n qubit, and then the second n qubit, right? So let's do this. So C4 after the first measurement. This is what gets very confusing. Of NLSB. So when I do measurement, can you tell me what will happen when I do a measurement on this superposition state? There's a lot of summation, right? Don't worry, just a lot of summation. Maybe 1 trillion times 1 trillion summation terms. And you do measurement. These are the basis state. What will happen when I measure the last n qubit? What happens when you do measurement in quantum mechanics? Collapse to what? Basis state. Very good. It collapses to one of the remainder. Why? Because this state is not any x, it's f of x. Okay? I only have f of x state here. It is not 1, 2, 3, 4, 5, 6, 7, 8. It is f of x. So, for example, right, for 11x mod 21, we only have these states 1, 11, 16, 8, 4, 2 in the last n qubit. Because it's only f of x exists. So you don't, do you have 2? No, because f of x cannot be 2 for this case. You never have a remainder of 2 as we calculated earlier. We only have this remainder 1, 11, 16, 8, 4, 2, right? Do you understand what I'm talking about? That is because we have the quantum oracle force this last NQ bit to only have these 6 possible values. Okay? So it will collapse to one of the f of x. So assume it collapses to f of x0, right? This is f of x. So let's say the first one is f of x0. We know that f of x0 equals to f of f0 plus r equals to f of x0 plus 2r. Right? Because it's a periodic function. So if you collapse to 1, then of course it's 1. However, this 1 associated with an x. This x can be f of 0, can be f of 6, can be f of 12, because its period is 6, right? So you have, which is f of 0, f of 6, f of 12. The reason I want to say that is this. When you collapse, then other function will be gone. But only those x give you the same f of x will exist. So C4 is going to be, and we don't do normalization, right? So I will just write down, I'm not going to keep the factor here. Because after measurement, you need to renormalize, so I just say it is proportional to this. First term, summation, k equal to 0, 2 to the power 2n minus 1. Right? Did I miss something? Okay, sorry. Write this in summation, k equal to 0, 2 to the power n minus 1. Right? This one refer to this term. This term is still there. But now you don't have FEX. You only have what? What are the x that exist? You only have x equal to x0, x equal to x0 plus r, x equal to x0 plus 2r. You only have this term left. And this is omega negative kx, k2n, and here is f of x0. This actually is f of x0, f of x0 plus r, f of x0 plus 2r, but I all call it f of x0 because they are the same. Maybe it's better I call this f of x. Maybe that is better, which is okay. Let's pause here. I know this is the most confusing part. Any questions? Yeah.
Why in the last equation in XL the second x0 plus
Yeah. R. Yeah, y
Or
can.
the other x.
So originally, you have fx, right? X to the 0 to the power 2 to the power 2n minus 1, right? You have 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way to 2 to the power 2n minus 1, right? But then you do the measurement. This measure, and so you also have f of 0, f of 1, f of 2, f of 3, f of 4, right? However, this is f of x, right? So it is periodic. You only give you 1, 11, 16, 8, 4, 2, 1, 11, 16, 8, 4, 2. Because this f of 0, f of 1, f of 2, f of 3, f of 4, f of 6, f of 7, and then again. Correct? So when I measure this, it will collapse to only one of the f value, f of x value. For example, it may collapse to 11. If this is 11, what are the possible x here? It can be f of 1, f of 1 plus 6, f of 1 plus 2, 6, f of 1 plus 3, 6. So only this will survive. Others will be gone. So regular when you do a measurement, everything else will be gone. Only the one you measure will be left over, right? You measure 0 plus 1, you measure it, it collapses to 1, then you don't have 0 anymore. And now the same, I have a bunch of number, I measure it, it will collapse to one of them. But the main point is f of x only has this value, is the remainder of that function. The remainder of function is not everything, right? So it will survive, but when it survives, it means your x either is x0 plus r, or x0 plus 2r, or keep going. I don't think it's clear. Any question, but you need to ask. I don't know how to explain more. Which part is not clear? Which part is clear?
The bottoms.
Not free. I write in this way so you have even more to infinity. So I'm trying to say x can be equal to x0, can be x0 plus 1, can be x0 plus 2. So it means that it's going to be this term, f of x0, plus this term, f of x0 plus r, plus this term, f of x0 plus 2r. That's what I mean.
So
Yeah. Yes. No, f of, let's say, f, okay, let's say f of x0 equal to 1. F of x0 equal to 1. So what are the x that can give you f of x equal to 1?
0.
0, 6, 12. Very good. So what I'm trying to say is that this is 1 because f of x equal to 1. Then what left over is negative k times 0 plus negative k times 6 plus negative k plus 12. Only this term left. But originally we have negative k times 0, negative plus 1, 2, 3, 4, 5.
First term. Second term.
The second term is whatever you have plus gamma, plus r, sorry. Oh, whatever you have plus r. Yeah. Sorry, that is the confusing part. What I'm saying that here is that summation, you take value from x0, x0 plus r, x0 plus 2 all the way. Yeah, that's what it means. So it's not a standard notation.
So can you rewrite it to x0 plus nt and put summation?
Relate to what, say again?
Instead of can you write it as
Yes. So I want to do that later. Indeed, it's just x equal to x0 plus nr, but n from 0 to the, I don't know what it says, right? Because r cannot exceed 2,000, nr cannot exceed 2 to the power 2n. But yeah, which I will do it in the next step. Okay, so I will stop here. I know this is confusing. If you have question, let me know.